All right, welcome back. I know 2 to 3 pages and all those things that I asked for are not easy to do, especially the time constraints. Really wanted you to get started. Let's take a look at what's going on here. I want you to take time and count the number of choices you think that exist within your narrative. Do you think every reader will have the same reading experience? If you go back and you take a look at your narrative, is there a possibility that a reader could get stuck within your narrative? Do you think you could extend yesterday's unplugged activity, where we talked about taking a task and unwinding it into smaller subtasks and abstractions? Do you think you could extend that activity based off of what you've just done? Would this task have been easier if I'd given you a topic? So here are a couple that I came up with. Writing a nonlinear narrative on the water cycle from the perspective of a drop of water. A self-driving car arrives on the ranch or a new town, somewhere where it wasn't designed to go. Maybe instead of self-driving car, it's the robot rover that was meant for Mars made it to let's say Pluto instead. What happens? All right, the history of human beings creating tools, or of a human creating tools. A game or sport, softball, football, cross country, from the perspective of a player or an athlete or the ball. Path of a red blood cell. Space explorer, Viking explorer, Wyoming settler, navigating between 2 points, for the first time to a new place. Would this have helped in your ability to write a nonlinear narrative, as opposed to me giving you a very open-ended task? Now, considering all these and the original task, let's go back and look at why these matter. So, first off, majority of programs, of software, of computational thinking that is interesting is nonlinear, right? A set of repeated tasks, I mean, it's fine. It's okay if it's just straight through. But where it becomes incredibly powerful is in decision making. In our ability to make decisions, we are much more effective at accomplishing great things. So programs need to have a starting and ending point. Everything in the middle might be completely different and might not look the same any 2 times the program runs, but they need a starting and ending point. If we take a look at the very first construct, very first thing that I asked you to look at, it was to give the reader a choice to do A or B. So if the reader decided to do something, so some condition, then A happened. Otherwise, else, B happened. So that's a pretty simple choice. If something is true, then do something else, do something else. All right, a lot of else's there. The next one was kind of repetition. It was a lot like what we saw in the very first unplugged activity. Do A, do the things in this little yellow block, do it until something is true, then do B. So basically you do something over and over again, repeat A while some condition is true, then move on. In this case, when we were a reader, the reader is controlling that condition. It's the reader that's making that decision. All right. The next one was having this number, right? The 99 bottles example. Do something some number of times is one particular way to look at that. Then go on and do B. So what this could look like is if you choose some number 5, do A 5 times is what this would be equivalent to. Then go ahead and do B. So the forced branches was a little bit of an interesting one, where one of the branches, one of the choices never happened. Right? We never did A. A was there, but we never were able to do it because something externally said that we We must always choose something. So a really simple example of this would be if the current day of the week ends in day, do this. Otherwise, do something else. Well, every single day of the week ends in day, so we would always do this one thing. We would never get to this other part. All right. So when does this happen, by the way? We're like, forced branches seem a little silly. So let's say that our if something is an always true statement. So if 1 is greater than 0, if blue is a color, if I'm older today than I was yesterday, all of those are always true. I'll always do this first part, and I'll never do the second part. The other version of that is if you had an always false statement. So 0 is greater than 1. Always going to be false. There are words that rhyme with purple. Always false. So this very first part will never ever happen. We will always do the second part. So where might we actually see this? Well, we actually see this because there's actually a common programming mistake that happens with many beginning programmers and actually not so beginning programmers alike. And it's when you assign a variable a value instead of comparing its equality. So in a lot of programming languages, we assign a variable by using an equal sign, and we compare two variables by using double equal signs. So let's give you a concrete example of this because I know that that's a lot. Let's say that I wanted to check if my thermostat was set to a number, 72 specifically, and then I would do something if it was. So here's the big condition statement. If condition, display smiley face, because 72 is an ideal temperature. Sure. Else, run change temperature, right? Because if it's not 72, I'd want to change it. Okay, so the correct way we would do this in code or in pseudocode here, but in code in general, if therm for thermostat is equal to 72. So this actually checks and asks, is the thermostat temperature equal to 72 using two equal signs? If that's the case, then we're going to display smiley face. Otherwise, we're going to run temperature change. The common mistake that most people make when they get started, because it is very different than how we do things, I'll say in traditional mathematics, is you would do equal sign here. If therm equal 72. It's because in math, a lot of times what you do is you would put a little question mark up there, and you would then have yes or no, or true, false. But in computing, we don't really have that. So this is what you'll do. And what will happen, unfortunately, is you will always display a smiley face. So if you were to write this code, you would come up with always having a smiley face. So if you wrote this code for the microbit and you tried it out, you would get a smiley face no matter what. The second part would never run. And you're like, well, why? Clearly, I'm not trying to set my thermostat equal to 72. I wanted to check it. Well, unfortunately, when you did this, the computer was basically asked to set therm, whatever that might be, to 72. So assign it, basically. Hey, I want it. It thought what you wanted was to set it to 72. It was successful at doing that because you told it to do it. So it returned true. Basically, it acknowledged, hey, I was able to do this. So the two things happen when you do this statement. Here, let me do a different color. The first thing that happened is if you imagine that there's some place in the computer where therm is there and it had some value. Let's say the value in here was whatever, let's do 70. When you ran this statement, what you actually did is you did therm became 72. And the computer, because it did this, was like, hey, I did it. So it actually says true. I was able to accomplish the task. So the result of this statement is two things. You can actually assume somewhere in the computer it's like last task. It's not really this. Status. And it put true once it did this. It did this check mark, said I was able to do it, so it set this to true. And so this is true always. Compare that over here. I'm going to put the same, I'm going to do the exact same thing. We have therm and last status, and this was 70. We don't really care what this was originally. We do this test here, if therm equals 72. So what it's going to do is it's going to check. It's going to look. Oh, what is the value of therm? It's 70. Is 70 equal, equality equal to 72? No, it's false. It never is actually checking this last status because it actually has an equality here. So, all right, in a nutshell, showing you that what you did in your story, in your narrative, really is equivalent to how computing systems work. So if you have any questions, feel free to share them, and yeah, make sure you take a look at answering these questions, analyzing your narrative, and really thinking about how you might be able to use this type of activity to motivate and have students start to think about how we process information, and ultimately how computers are processing information and making decisions, and the types of control we might have over a computing system. So all of the things that I've mentioned are ways that we can control how a system, a computer, a robot, will do activities. So this in combination with the activity from yesterday is really the nuts and bolts of what computer science is all about. It's all about problem solving using control structures like this and explicit tasks that are well defined and, if possible, abstracted. All right, so with that, enjoy your next activity session on the microbits.